So now that's it. Now we have the, so we go to the lab now. We are going to form the experiment and see whether the period is actually connected with the length, and that the amplitude has no business with the period, we know that, or the mass of this bulb has no business with the period also. So we will try and verify that. So we check this again. We are moving. So the first thing I'm going to do, because of I want to get a correct experiment, I want to get a correct result, I have to ensure that I take some precautions, and those precautions could be based upon the materials I'm going to use. So the uncertainties that will make my answers or my prediction accurate is based upon the fact that I take some precautions as I'm moving on. It is relevant to say that I cannot exactly get the length here because I'm taking the, I did not measure the radius of this bulb, so that this my 80 will not be exactly 80. So I can say that there is an error or an uncertainty in the length, which is based upon, let's say, plus or minus 5 centimeters. I'm not too sure because there's no way I can get it exactly here because I didn't use a caliper to first of all get a radius to add it to that length such that I'll have exactly 80 centimeters. So there are all some uncertainties here. So to minimize those uncertainties, that is one way that my experiment can be affected. So I'm going to make sure I minimize most of them. That is the more reason why I'm going to do one or two. I'm going to repeat the experiment and take average to help me out to reduce some of the uncertainties and the errors I will be expected. That is based upon my, and again, another source of uncertainty or error will be based upon my own human factors. You know, my reaction time to stopping the watch will be also a factor. So I'm going to ensure that I'll discover first my reaction time. You can do this as a student if you want to know your reaction time before you do this experiment. You try to know your reaction time first of all. This may not be accurate because if I want to get it properly, I'm going to ensure that I give the rule to somebody, and I'll be the one catching the rule as it is running down. I'll be able to just try to hold it as it is falling, but for now I'm going to do it myself. And in the practical case, if you want to actually check your reaction time, you can do this experiment with another colleague. So you tell the colleague to hold the roll somewhere there, that is the zero displacement, that's the zero mark of the meter roll over there, and you are trying to see your reaction time because you're coming to press this, and your reaction time is also a factor to all these variables. Yeah, I've just eliminated this one here. I say it could be somewhere plus or minus 5 centimeters. What about the human factor? The human factor, it's how do I respond? How am I going to press this stopwatch to get accurate reading as the pendulum is going to complete the oscillation? At the moment, the oscillation, the time will be pressed before the complete cycle. So all these factors will affect. So I want to see first of all my own reaction time to event. So this is how you calculate your reaction time. So if you want to try this experiment, try to get your reaction time first so you know the values you are bringing, whether they're accurate or close. So check, this is how you do it. You get a colleague to hold the rule for you, and he's not going to tell you when he's going to drop it. You'll be looking at it and you try to catch, he's not going to tell you when he's going to release it, but if it's possible that you can really concentrate and look at the man and try to see when he's about to let this roll, then if it's possible that when he lets the roll and you are able to capture it somewhere there, that is, let's say I was able to capture it around 50 centimeters, let's say in the middle. I did it myself, so this may not be accurate, but if you want to do it, we want to do it accurately, you try somebody else so that you can actually identify your reaction time. So now let me see, let's take for instance this is my reaction, this is my position where I was able to, somebody must have let it go, and I was lucky to just by inspection I just was able to grab it. When he let it go, I was able to, it's possible that the rule can even drop, you miss it, but you try it over and over, you'll be able to catch the rule at a point. So let's say you are able to catch it somewhere here. Like for this, my example, I'm able to catch it at 50. So 50 centimeters. So for 50 centimeters, I want to now look at the equation to find my reaction time. So for us, calculating my reaction time, so that this will help me to see whether I'm going to get a correct example, practical over here. So the reaction time is, I have all the position, which is the S of this rule. The rule fell a distance of this 50 centimeter, let's say 50 centimeter, which is 0.5 meter to that end. That's where I was able to capture it. It's possible that you capture it at 80, at whatever number here. So let's say that's my number. Now I have that. So when the rule was at rest here, it was in equilibrium. It was at rest initially. So the initial velocity is 0. So the initial velocity is 0 there. And now there is a time for which it dropped, and I was able to catch it somewhere. There was time within that period, and it was falling inside gravity. So, and gravity in this studio is going to be, let's assume it to be 9.8 or 10, let's say 10. So now we have this. So this is the equation. The Newton was able to help us with the reaction time, sorry. So now we have this equation. Since this rule started from rest, it means that it must have got an initial velocity of 0. So the initial velocity here is 0. So this whole statement is 0, and we have half AT square. And in this room now, the acceleration was due to gravity, because when I let it go, it was the gravity that was pulling it down. So acceleration is due to gravity. So I have half GT square. Now if I do the math, I have 2h. Let me say this is now the height to which is falling. That's the distance. So I can say h is half GT square. So I have GT square as equals to 2h. Now we have the g there, and this is g here. So t can be root of 2h all over g. So if I can calculate this, I'll now substitute the variables in the values inside. Is 2, the height to which the rule fell, where I was able to capture it, is somewhere there. Let's say it was in the middle, so it's 0.5, that's 50 centimeter, that's 0.5 meter. And let's say acceleration due to gravity here is something like this. So I have t as equals to, so you have 1 divided by this. So you can use your calculator. You can go along with me. We use your calculator and see what we can get here. So this is, let's just punch that from the calculator. This will give you, now it's 2 times 0.5. That's 1 divided by 1. This is 1 divided by, so you can have something like 9.8. So I have, so you can use your own calculator, is 0.102. So 0.102. If you take the root of that, you have something like that. So let's say we want to take the root. I've just multiplied this by this and divided by that. That's the g. And I want to take the root of that. So you can have root of 0.102. So 0.102. So I'll be able to get approximately, let's say 0.3. Yeah, so this is plus or minus. My reaction time is 0.3. So my time, the values of my time would be as within an accurate limit of plus or minus 0.3. That's my reaction time. So whatever I'm going to do here, the time I'm bringing out, I'm going to record here will be within an uncertainty of plus or minus 0.3. So that's my own reaction time. This is not accurate because I didn't do it properly. Somebody was supposed to hold the roll, then I drop it all by myself. But this one was done just roughly because I wanted to just demonstrate it for you. It was done by myself, but by all indication, it's possible that my brain must have told me that you are about to drop the rule, so I'll capture the rule. But if I'm doing it with somebody else, it's going to be a number that is going to be less than this. But when I did it with somebody else, my reaction time was around 0.2. That's in reality, my reaction time was 0.2. So that's my reaction time. So whatever value I'm going to record here, let's say I say my reading for the time recorded, you'll be able to tell me that I'm going to be within 19.8 or 20.2. So that's my reaction time in real sense. I've done that with somebody else, but for this experiment I just did it for you to understand how to get your reaction time. So now you now know your reaction time. Now you can, we now try to look at the experiment proper. So I'm coming to investigate how the period will affect, how the period is affected by the length. So I have done a couple of experiments over there. So let's see. Now I have the length. Let's say the first length there I've said is 80, 70, 60, and I can put this length in meters. This was in centimeter, so I can put this length in 0.8 and 0.7 and 0.6. So here in meters. Now I'm coming to find, remember the period is given by 2 pi length over that. That's what I'm trying to investigate. Whether the period of oscillation of the simple pendulum is directly proportional to the square root of the length. We want to try that. So now let's go to the experiment. I'll be able to give you a kind of an explanation on this. This is a meter rule, you know that already. This is a retort stand, and this retort stand has balls. That's the ball, that's the clamp, and you have the cork, and we have an inextensible string, and that's the ball. I have explained this already. So prior to this experiment, I was able to measure this length, the length of the pendulum. The effective length was, I've taken it to be, this is around 80 centimeter. So 80 centimeter, this is 80 centimeter, this other one is 80 centimeter, this one is also 80 centimeter. So now I'm trying to do the experiment and try to see what will be the time for complete oscillation. So I'll displace the bulb. Remember, I said that when you're about displacing the bulb, you must ensure that the displacement, so that you don't commit the isochronism. So you have to move here so I've already marked here. So let's say the displacement is here, so I was able to measure it here. It's around, you said 13 centimeter from the equilibrium position. So 13 centimeter is somewhere here, and 13 centimeter is somewhere here. That is 1/6 of this length. So 1/6 of this length gives me 30 centimeter, so that I will not go out of this range. If I go displacement too much, I'm going to ensure that the period is affected. So now I want to just give it a small displacement. So now let me just measure 13 centimeters somewhere around here. So if I have to mark it on my table here, I'll get it here. So that's where I can displace it, and I can also displace it here. That is for the length of 80. So I'm coming to displace it this way or displace it this way. So it could give me the same stuff. So now we go. And remember that the stopwatch, you have your own stopwatch, but I have a stop clock here. I have a stop clock. I have set it to 0, so it's a stop clock. So on this stop clock, I'm going to allow this pendulum to swing for some time. To get it accurate, I'm going to allow it to swing for some time. So now I'm going to displace it at 1/6 of this length. This length is 80 centimeters, so I started with that one. So I'm coming to displace it at an angle at 10 degrees approximately there, but based upon the adjacent here, I'm able to look at it as being 13 centimeter. So this is my 13 centimeter. This was 13 centimeter. So I'm going to ensure that I don't go beyond this 13. So that is where I've be able to figure out, because this is 13. So I measured the 13 somewhere there. That is 1/6 of this length. I measured 1/6 of this length over there, so that I can not exceed this point. So let's say that's my point. So now I need to figure it out there so that I can go beyond that. This is 13 centimeter from here. This distance is 13 centimeter. That is 1/6 of this length. That's 13. So now I'm going to ensure that my bulb does not go beyond that. So it's somewhere there. I cannot go beyond it. It's got to be just there. So now this is the displacement. So that is a relevant one to ensure that I'm within that limit. So when I've already got my mark on this, so I can put it there and allow it to swing. So the best way you can do this is to allow the bulb to swing for some time. Then you now try to get your time. This is 0 for now. So I'm going to start from here. The moment it starts from here, it goes and comes. It's 1 oscillation. So I'm coming to do it for 20 complete oscillations. So you count along with me. Let's go. Student, let's go as we count. Now I'm coming to start here. So the moment it comes here, I'm going to start. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I'm able to get somewhere something like 36 point. This is somewhere 36 exactly. That's 30. It's just a little. It's between. It's just exactly on 36. So I'll be able to get 36 from here there. So now I'll register 36. There. This is for the first time. So in seconds, my first period was my first time was 36 seconds. So 36.0 seconds. Now there's possibility that because of my reaction time, remember my reaction time. So this one will be somewhere. It could be 36.02 or 35.8 is possible here because of my reaction time. Now I want to still eliminate. I want to be within a limit of perfect experiment. So what I will do is to do it twice again to see. Another time I'll do it again to see whether I can get the same time there. So I'm going to start again. So students, be prepared. Let's go again. This is there. It is in its equilibrium position. So I was able to displace it at an angle at a displacement of 1/6 of this length. That's it here, so that I don't commit isochronism. So that is here. This is now 13 centimeter. Is still there. So you can always verify to ensure that you're there. This is 13 centimeter. So now this 13 centimeter is somewhere there. So 13 centimeter there from the equilibrium position. What I've done is this is 13 centimeter, so I move it again. I'm coming to repeat the same 80 centimeter. I'm going to do it for another time. This there, I replace there. So this is there, so that I can't go far. There, I know that this is now the displacement, so I allow it to go. So it's I allow it to swing for some time. Then I can reset my timing. So it's 60 degrees, 60 at the 0 there. So I'm coming to start here. So I'm allowing to swing. When it's 30, come here now, I start. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So here is it again. So exactly, let's say that is between 35 and 30. So we'll see this is at just a little there, just around 35 points, just somewhere there, 35 point something, between 35 and 36. So it's closer to that. So you see, because of the reaction time, it's possible that you can have something like that. So this is 35.6. So 35.6. So this is second time. So I've got that for this reading. So I'm coming to do for the 70 now. So I've prior to this, I've already ensured this was 80. Now this is 10. That is 70. This is 60. So I was able to measure that with the rule. So from the center of gravity of that bulb, I was able to figure it out that this was 80. This is at 80. So this other mark here I've made before, that was 70. This must be 60. This must be 50. So I'm coming to now adjust so that I can get 70 centimeter. The first one was 80, so I'm coming to do 70 centimeter. So I move from that point, 70 centimeter. I can just adjust this easily. Here it's easy for us to adjust that. So I just undo this. Then I try to load the mark I made here for 70. This one was 80. Now I'm going for 70. I just adjust it so that I can get 70 there, just there. Okay, so it's there. So I come to fix it so that it is avoid random error. It's here. This is it. It goes there. So I've already got, this is 70 now. We want to verify that very well. So it's from the center of gravity of the bulb there. Yes, this is exactly 70 centimeter. So it's 70 centimeter there. So now 70. So it is 0.7 this time. So I'm going to take 70 centimeter. Now 1/6 of that, if you punch that from your calculator, you will have something like 11.6. So it's 11.6. So it's approximately 12 centimeter. So now I'm going to displace it. Remember, this was 11 here. This was 13 for 80 centimeter. Now it is 70. So I'm coming to, it should be now, the displacement must be now 12 centimeter. So I'm coming to, I've marked it initially. This is there. It's 12 centimeter somewhere here. So I'll just now put my rule somewhere there. So that's 12 centimeter. This was 13. Now this is 12 centimeter. So 12 centimeter there, so that I will not exceed this. So it's going to be just there. I will not exceed it. This is 12 centimeter, somewhere there, here, so that I will not exceed that. So this is the equilibrium position. I bring it now to displace it again. So this is 12 centimeter here. So I displace it, I leave it to oscillate. Now, as it is oscillating, I can come and do my timing. So I allow it to swing for some time. Then when it comes this way, now I'm starting from here. There, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So here, this is, you can see from there, it's this is 34. This is between this 30, 31, 32, 33. This is 33.5. This is 33.5. So it's 33.5. So he's gone through 33.5, 33.5 here. So now 33.5 has gone that. So I'm coming to do it, repeat it again for not the same, the same 12 and the same 70. So I'm repeating that. So I go, this is, I already know the position. This is T12 here. So I will do it a little bit faster now. So this is, let me start again. This is 12, right? So allow it to swing. Right, you can see that it's a straight line motion, like I described it before. So I now have here. So can I allow it to start here? So we continue. So when it start here, I start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yeah, see my reaction time. It's like, like I gave you, so you must be able to look at it. This is somewhere here, this is 31, this is exactly 33. This one is 33, exactly on 33. It's now 1, 2, 3. So because of my reaction time, I have all of these different numbers coming. So it's 33, that case, 33.0. So now we have that. So I want to do for 60, that's one there, 60. So this was 50, this was 70, now this is 60, I marked it. So I can undo this a little bit. So now I have, yeah, so this is 60, the mark has been made there already. This is 60, the mark was there. So I have, yes, that is 60. Now I do try to make it firm some way. So here, yep, so I got my rule to confirm that very well. So this is from the center of gravity of this ball here is that 60 centimeter. So 60 centimeter here. So 60 centimeter. It's 60 centimeter. 1/6 of that is 10 centimeter. So here, come back here to measure 10 centimeter. This is 10 centimeter from the equilibrium position. That is 10 centimeter somewhere there. So I'll put my ruler here. It's 10 centimeter. Right. So now I can just lift it a little bit so that I don't move away from that. That is 10 centimeter. Yeah. So 10 centimeter there. Allow it to go. So now I set my time. So start as it is starting here and go. I'm going to start when it start here. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I was late a little bit, but this is 31 point something. It's 31 exactly on 31 point something. So I was late a little bit because my reaction time, remember that this is okay, let's say 31. This is 31. So it's 31 somewhere here. This is 31.0. So I gotta do it again. So that's it. I was a little bit late to stop the time, but it's possible because of my human factor some way. So I just go there again. This is it, the same angle. That's it. I bring it right there. This is 10. Yes. So here I allow it to go. So it's going. Then I can restart my time again. So start from here. When it starts here, I come. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So here, see, this is 31 exactly. This is 31 exactly. So it gave me 31 there. So we're going to get 31.0. So now I've got the 3 readings. So these 3 readings can help me to do something here. So I'm coming now to find the period. And this is, remember the number of oscillations. My number of oscillation was 20 oscillations. Yep, so now I'm coming to, I want to make sure my readings are correct once I go to that point. So I'm trying to find the average. If I find the mean or the average, so if you can call it the mean or T average, you know that when you find an average, you have to add the 2 values and divide by 2. That's the average between the 2 guys. So I'm coming to add all of them. Of course, this one is 31. So you use your own calculator. In the exam, you're not required to use mobile phone, but don't mind me. This is 36 plus 35.6, 35.6, 6 divided by 2 is 71. Sorry, this is 71.6. So 71.6 divide 2. So you have 35.8. So you can get 35.8. This is 35.80. So this is 31.00 if you like, and this is I punch the other one. So you use your calculator. So I'm just trying to 3.5 plus 33.0. You have to do this during the exam for yourself. So that is 66.5, 6.5 divided by 2. So I have 33.3. So I have 33.3. It's 25 actually, 3.25. So we can say 33.3. So now that is the mean. So we want to find the period. The period is T average over mean. So remember that frequency is number of times something is done over the period. That's what I was doing, number of times. So the period is the reciprocal of frequency. So you can say this is 1 over n over t. So if I do the math, I'll now have t over n. So that's how the period became that. So that is dividing by 20 complete oscillation. So now I use all of that. So it's easy for you to understand. I believe you are understanding as I'm moving. This is so we're coming to divide these numbers by the number of oscillation. T average here, that is adding this and this, divided by 2. That's how I got the average. So this average is what I'm divided by the number of oscillations. And that number of oscillation keeps changing based upon the question. So in this question, we are using 20 oscillations. So we are dividing 35.8. You divide along with me as well. So to get the correct figure, if you like this you have 17.9. So I have 17.9. This is 17.90, let's say. Now we have the next one there. We'll do is now we have 33.5.25 divided by 20. Divided by 20. This is 1.66. That's an error here. This is 33, I go back there. This is 1.66. So there was an error somewhere there. She gave me a wrong figure. So it's 35.80 divided by 20. This is 1.76. This is 1.76. All right, so now I come back here. This is divided by 2. This is 15.5, if you like. This is divided by that. Let me just do the math there. You also do the same. So 31 divided by 20. So 1.55 is 1.55. So basically, this is what we are required to do. You see, I'm doing it slowly so that you understand. That day, it's going to be your own tongue.